Okay, so welcome back. Next up, we're going to be talking about the binomial distribution and why it is useful in engineering, right? So the binomial distribution is a discrete distribution that describes success and failure of a number of trials, and each of these trials is independent, right? And so one of the first things that we probably want to talk about when we talk about the binomial distribution are some ground rules, right? And the ground rules for the binomial distribution are that the sample includes n occurrences, the n trials are each independent, only two outcomes are possible for each trial, and that probability is constant from trial to trial. So a question might be that you're trying to think about right now, what are some good examples of this? And so the classic example of the binomial, applying the binomial distribution is coin flips, right? So let's look at how coin flips apply to our ground rules here. So we might flip a coin 10 times, right? So we might have 10 occurrences, right? And I know that each coin flip is independent, right? Just because I got a heads last time doesn't mean that I'm more or less likely to get heads or tails this time, right? So each trial is independent. And there's only two outcomes possible. You can either get a heads or a tails with a fair coin, right? And then the probability is also constant from trial to trial, right? So we're assuming, right, that the probability is 0.5 to get a heads, and it's 0.5 to get a tails, right? And it's constant for every trial from 1 to infinity. Okay, so let's look at some engineering examples of this, right? So what are some good engineering examples? Well, one example is how we could apply it is thinking about flooding, right? So we'll kind of go over two different flooding examples in engineering. The first is, this is a picture of Darlington. And so Darlington has had a long history of flooding issues related to the Pecatonica River overflowing its banks and at times completely flooding out the downtown portions of Darlington, right? And so managers, they might be concerned with something like, what's the chance of a large flood that floods our downtown occurring this year and next year in Darlington, right? And so for budgeting issues, maybe they always have enough money in the bank, right, to deal with one flood and all the costs associated with that. But if they had two in a row, that might be a real challenge for them to meet, right? So they might be interested in the probability of two large flood events occurring in a year. And then they may make changes to how they budget money in the future if it seemed like it was more likely or less likely, right? And so in this sense, we're kind of talking about modeling these things that we call return periods and the probability of occurrence and sequence. And we'll talk more about that as this part of the lecture goes on. So another case that we might be interested in is, let's say we're doing bridge work. So here's a picture of a bridge work being done in the Mississippi near Winona, Minnesota. And we've got a cofferdam that's been put in place. And you can see workers, they've got access to the riverbed, and they might be putting in a new pier here, right, to hold up a bridge or something. So we might want to ask, I'm building this cofferdam around a bridge pier for work. Right? Over the next year or month, or whatever, what is the chance that this could get overtopped, right? What's the chance that the cofferdam, that there could be some flood of a certain magnitude that would overtop the cofferdam and either maybe, result in some sort of hazardous work for the workers there, or could actually, destroy, cause failure in that dam and maybe, end up causing failure in the pier that we're putting in. Right? So in this case, we're trying to model what we call risk and reliability. And both of these things, modeling return periods or modeling risk and reliability, can be modeled using what we call a binomial distribution. So when we talk about probability in the binomial world, right, we're talking about the probability of having X successes by N minus X failures, right? So we've got the total number of successes minus the total, and then we've got the total number of trials, which is n, minus by those successes. Those are the failures, right? And it's the product of the probabilities of what we call n independent events. So what does that mean? Well, mathematically, we can represent this as the equation that you see here. So you want to probably scribble this down in your notes, right? So here what we're saying is that x is the number of successes, N is the number of trials, and P is the probability of success for each trial, right? So when we're talking about coin flips, if I do 10, let's say I do 10 flips, that's the number of trials, right? So I could put 10 in where N is, and I know that the probability of getting a heads is 0.5. So I would put 0.5 in for P, right? And then the question now becomes, well, what is X? And it might be what we're interested in. Maybe I'm interested in getting one head out of 10 trials, or one tail out of 10 trials. Or maybe I want 3 heads out of 10 trials, right? So we can put those numbers into this equation and we can solve it. Now, the caveat with this is that this represents just one possible sequence of events, right? Just one possible sequence of events. And so in order to start thinking about, well, we might not be interested in just one sequence, we're interested in all sequences, we need to use something that's called the binomial coefficient, right? Okay, so we've just answered what the probability is of having exactly X successes in N trials for one sequence of events. So you could think something like head, head, tail, right? We're looking at just that specific sequence. But what if we want to know about for all sequences? So now we're talking about head, tails, head, and tails, head, head, right? We're talking about one tail and 2 heads, right? So we might want to think about all the different sequences that's possible. To compute this, we need to apply something that we call the binomial coefficient. And so here we can see it's abbreviated as n over x in parentheses or combine. And we've got n factorial over x factorial times n minus x factorial. Now, sometimes this is hard to put into your calculator, so we'll talk about it in class, some kind of workarounds to deal with this. But this is our binomial coefficient. So to put it all together, right, if we want to compute the probability of any one sequence and the number of ways in which such a sequence can occur, we use this equation here where we've now combined the binomial coefficient and we multiply it by basically our equation that we came up to represent the probability of x successes by n minus x failures, right? So there we have it. Now, the interesting thing about this equation is that this is the mathematical model of the binomial distribution. So if you recall from the last lecture piece that you watched, we talked about why we can collect observed data, but sometimes we might want a functional form or a mathematical form of an equation that we can fit to that data that we collect. So in this case, this is a model of one of those distributions, right? And this model has a mean of n times the probability and a variance of n times the probability times 1 minus the probability, right? So this is you could actually, in Excel, put in the mean and variance, right? And we could randomly generate, kind of a bunch of things. And we could look at, for any different types of number of trials and the probability, we could look at what this binomial distribution looks like. So it's kind of neat. And we'll talk about that more when we meet in class. So in a minute, we're going to do a few examples together, and we will do some more when we get together in class. But before we do that, and then we're going to follow it with some examples. Then this chunk of the lecture will end. We want to define this thing that we call return period, because it's got a very important meaning when we talk in terms of hydrology, hydrologic statistics, right? All these things, right? So return period, and here's kind of a funny little comic that you have in your notes. I said, an ark, you fool. I said, build me an ark, right? Not an arch. And so, in Noah's case, right, he's left with this thing, this flood of great magnitude, right? Maybe, this thing really occurred, right? We might be talking about a flood that's like the 1 in 100,000 year event. So what does that mean when I say something like that? What is 1 in a 5-year event, 1 in 100 year, 1 in 100,000 biblical type flood mean, right? So that's what we call a return period. So an annual maximum event has a return period of t years if its magnitude is equaled or exceeded once on average every t years. And so we're talking about equaled or exceeded once on average, and that's the key thing here, every t years, right? We say 1 over t is the exceedance probability. That is the probability that the event is equaled or exceeded in any 1 year. Okay, so what does that mean? What does that mean in terms of this class and what we're talking about? Okay, so think about this. A 100-year storm is the storm that has a 1% chance, oh, my notes are wrong there, it should be 1%, not 0.01% chance, of occurring on average any given year, right? So 100 is our years, right? And we're talking about that event that happens on average once every 100 years. That means it's got a 1% chance of occurring on average in any given year. Okay, so let's apply this to some examples here. So if you flip to your notes on the back of one of your pages here, you should have a sheet that's got a number of examples, and we're going to go through a couple right now together. So let's do the first one. You should look and you should see on the right-hand side of your notes that we've got a table, and it's got some different years and some maximum flow, right? And so in the first question, we want to know the flow that's 100 CFS or greater in 10 years. What's the probability of getting a flow of 100 CFS or greater in 10 years? So I'm going to give you a minute to kind of think about it. So I'm hoping that I'm interrupting you probably while you're thinking about it. That what we want to do is we want to look, right? We want to look at our table and find all the years that have 100 CFS or greater, right? And so in this we'd look through the table here and we'd count up the number of years that we have, right? And it looks like we've got 10 years of data. And we've got 3 years that have flow greater than or equal to 100 CFS, right? And so in this case, a probability of that occurring given our data set is simply 3 over 10, right? It's 30% chance of happening. Okay, so let's go to the next example here. We want to talk about what's the probability of one head from a fair coin in 5 trials. And it doesn't matter the sequence. We're not talking about a head at the beginning and that's it, and then the rest tails. We're talking about in your 5 trials, you could have a head occur anywhere in those 5 trials, right? So what we're talking about is something like this. We've got tails, 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 head, tails, 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 head, tails, 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 head, tails, tails, and so on, right? So we want to know what's the probability of this happening. Right, so here's the situation where we're going to need to use both the binomial coefficient. You know, we need to in our probability model for the binomial distribution here. We want to put these things together. So let's look at how we can do this. So we're going to say the probability of this happening is our binomial coefficient given 5 over 1, and so you should write this down, right? And you can plug 5 over 1 into the mathematical equation for your binomial coefficient, right? And then we want to multiply it by the other chunk of our binomial distribution equation here, right? And so we've got 0.5 in for P because the probability of getting a tail or a heads is 0.5. And we're raising it to the 1 in this case, right? Because we're talking about 1 success in 5 trials. And then we've got 1 minus the probability again, raised to 5 minus 1, right? And so here we've got 5 minus 1, where 5 is the total number of trials, and x is 1 because we have 1 success. And if you compute this out, you should find that you get about 2.5%. So now, right now here, we're going to talk about this in terms of something we might be interested in as an engineering question. What's the probability of a 100-year storm occurring once in 25 years, right? So once in 25 years. So let's look here. We're going to have, we got to figure out the number of successes. So here I'm going to guess that the number of successes will be 1. We're talking about something happening once. And we've got the number of trials is 25, right? We've got 25 years. So now the question becomes, what is the probability? And if you think back to return period, we said the probability is 1 over t. So in this case, it's going to be 1 over 100, or it's going to be 1%, or 0.01, right? So here we go. So let's look. We've got 25 years is n over 1 success. We put that into our binomial coefficient equation, and we're going to take that and then we're going to multiply it by 0.01 raised to 1 success times 1 minus 1% raised to the 25, because we've got 25 total trials minus 1 success, right? And if we compute all that out, it turns out that the probability of a 100-year storm occurring once in 25 years is about 20%, right? Okay, so I'm going to leave you to do part 4 of your example. So spend some time now working on that, and then when you watch the next lecture, we're going to talk about risk and reliability, and that'll end everything that's part of lecture 1.